Hello, everybody. This is a video on waves. I'm going to overview the rules of waves and then harmonic waves all in one. This is just a quick notes. Rules of waves. For a review of this, I also have the worksheet. And a wave, first of all, is the vibration of molecules that's passed from one to the other. Now, if I vibrate this up and down, that's some frequency F. Frequency is the vibration of the molecules. It's measured in hertz, which is repetitions per second. That's the input. Along with how high I vibrate the molecules up and down, which is called the amplitude. So if I vibrate this one up and down, this one goes up and down. So the rate at which I vibrate them up and down is frequency. The height at which I vibrate them up and down is amplitude. So I'm going to use this to mean distance, this to mean motion or rate. So this is the input or the actual motion of the molecules. The molecules don't move forward. The shape does. The vibration does. So the vibration moves forward at some speed v, which means that there is some response. There's a delay, meaning this one right here will, a certain amount of time later, vibrate up and down at that same frequency f. The intermolecular forces between the molecules determine the speed. This is determined by the medium. Don't just repeat that. Make it make sense. Right? We want that to make sense because we're going to change the mediums and we're going to want to think, how does that change the speed? So if I have a tighter string or stronger forces that connect these, I think it should make intuitive sense that stronger forces, stronger intermolecular forces, I'm saying that with my words, so if you're watching this video, IMF is intermolecular forces, or tension in a string, IMF in a solid or liquid means faster. So frequency is the input. So if I sit there and I make a note, or if I sit there and like literally vibrate a string, that's the input. But how fast it moves forward is completely dependent on the medium, specifically the intermolecular forces, and also the weight. Obviously, if it's denser, it's going to move slower, but if there's stronger forces, it's going to move faster. So that's a good summary so far. That's what a wave is and kind of how it works. Now, the rules of waves are basically that. One is V depends on the medium. Not frequency. Right? So if I double the frequency in a wave, I could have one wave that has a wavelength. The distance between peaks is the wavelength with some frequency f and some speed v. If I double the frequency, the speed stays the same. What ends up happening is I have twice the waves in the same amount of distance. So you're going to have half the wavelength. Right? So frequency and wavelength are inversely proportional. And V is constant. Now, this is if you're in the same medium. So same string. If I, in other words, vibrate the air at a higher pitch, it doesn't make sound go faster. It doesn't make the wave go faster through the air. It just makes the molecules vibrate faster. Just be careful. There's the vibration of the molecules up and down. And then there's the motion of the wave forward through the medium. Those are two separate things. So if I make the molecules vibrate faster, that doesn't make the wave go forward. Same velocity through this medium, if it's the same medium. Cool. Second rule of waves is if it changes mediums, it meaning a wave, then the velocity must change. Of course it must change because look at rule number 1, the velocity is dependent on the medium. So if I have, this is the, on the homework, if I have a heavy slinky and then a lighter slinky, this is a lighter slinky. I'm trying to do dotted lines here. So heavy, light, right? Lighter will be faster. And this will be slower. But you can think of these molecules vibrating up and down. If I were to vibrate this up and down at some frequency f, so slower V1, faster V2, we'll say V2 is greater than V1 because it's less massive. But with the same tension. Let's keep the tension constant. I can change the tension, I can change the mass. There's an equation for the velocity. Velocity depends on the medium. V equals, for a 1D wave only, right? There's one for 2D waves, 3D waves. There's one for gases, one for liquid. This is just a 1D string. It's the square root of tension over what's called linear density. Density is mass per length, right? That's important, but that is on the worksheet as well as going to be overviewed on the homework and in class, but just to have it in the notes right now. So obviously, if I have constant tension in these slinkies, but one is more massive, more mass means it moves slower. You see that inverse relationship there? Cool. Faster for a lighter mass, the frequency stays constant. Meaning, as the wave progresses and this vibrates up and down, and then this one vibrates up and down, and then this one vibrates up and down, and a certain amount of time later, this one vibrates up and down, all of a sudden the frequency doesn't change. Only the velocity changes and the wavelength. And the velocity is proportional to the wavelength. Right? This is a direct proportionality. So if I triple the velocity, the wavelength triples, but the frequency stays constant, meaning as the wave goes from one medium to the other. So if I make a wave in a guitar string, when it enters the air, the frequency doesn't change. And when it enters my eardrum, the frequency doesn't change. So I hear that A note. It doesn't change frequencies depending on medium. And that should make sense because these molecules are kind of dancing together at the boundary. So the way one moves, one has to move with it. Otherwise, the wave wouldn't be coherent. It would deaden, it would stop, right? And the wave does stay coherent and the frequencies stay together. So that's just a quick way of explaining it, easy way to remember it, keep it easy, keep this sorted. This is important, whatever you have to do. Great, that's the rules of waves. So now